That's it. Right. Start again.
Okay.
Go
again. I'll just talk through very quickly how we've done the first part. So we have 500 metres of fencing that are going around this shape, and we want to maximise the area. So firstly, we've got to come up with an equation for y. Show that y is this. We can see we've got 2x plus y, and then plus the circumference of this part here. So the circumference of the circle is 2 times pi times r. So I've got 2x plus 2y plus the circumference. That would be for a whole circle, but we've only got half a circle. Okay, I've collected like terms and simplified it, and then I'm rearranging to get y by itself. Okay, so we've got 2y, and then we divide both sides by 2. Okay, so that's part A. Part B, show that the area is this equation here. Well, the area is going to be the area of this rectangle, right, plus the area of this semicircle. So part B, the area, we can make an argument like this, rectangle plus semicircle. Alright, so the rectangle we can see is 2x times y. And the semicircle, well, the area of a circle is pi times r squared. And so for a semicircle, it's going to be pi r squared on 2. And our radius is x. Okay? And the reason we came up with an expression for y is so that we can plug that into here to just have one variable in the problem. So when I bring y over here, I'm going to have 2x times y. I'm bringing that whole thing over. We've got 250, should be not 200, 250, take x, take pi on 2x. Okay, we've got 2x, y. Okay, and then plus the semicircle, pi x squared on top of 2. Okay, we're going to expand this and then collect some like terms. So here we'll have 500x, take 2x squared. That's going to be take pi x squared. Okay, 2 times pi on 2 becomes just pi. And then we have plus pi on 2 x squared. Alright, so looking along there, okay, these aren't like terms, but these two are. Okay, they have the same x squared, and they're both in terms of pi, so we can actually collect them. I think a good way to think about it is it's minus pi plus half of, minus pi x squared plus half pi x squared. Okay, we've got minus 1 lot of pi x squared plus positive half of of pi x squared. So that's going to leave us with negative half pi into x squared. Okay, you can think of this as minus 1 plus half is minus half. Alright, pi on 2 is half. Let's even write it like that, minus half pi x squared. That's fine, we're absolutely fine to write it like that. Okay, they're like terms, we collect them, that's what we get. And that's what the area is, isn't it? Whereas show that the area is this. Okay? Exact same. So another 2 marks there. And then part C, using calculus methods, find the exact area that maximizes the, find the exact value of x that maximizes the area of the shape. So we can know already for our sine diagram that it's going to be a maximum. Okay, so we can just go straight to the sine diagram there. We don't know this value yet. We're going to find it exactly. One way we could do it is to graph our area function. And if we do that in a moment, we'll be able to g-solve the max. Okay? Nonetheless, this is our area function, right? So let's find a dash of x. Okay, if this is the area, then the derivative of this is going to be 500 take 4x, and that's going to be take pi x. Alright, we have 2 times half is 1, and x squared becomes x by itself. Okay, so that's the derivative function. Now to find the x value of the turning point, we need to go what is going to make the derivative function Okay, we're trying to find when that equals 0. So what we want to do is isolate the numbers and isolate the x. So I'm going to move both of these x terms onto that side. Alright, we're going to have 500 is 4x plus pi x. Okay. X is common to both of these terms, so I can factorise it on this side. And 4 plus pi is just a number, so we divide both sides by 4 plus pi. Right, what's pi? About 3.14. So this number's roughly about 7. And so we can see we've got x by itself, it's 500 on top of 4 plus pi. Okay? There we've answered it exactly. That is the exact value of x. 500 on top of 4 plus pi. Okay, and then we should answer the question. We can just say the max area occurs when x equals 500 on top of 4 plus pi. Okay, so it's quite a hard one. I'm going to talk through it again. Alright, and the question is almost identical to this, but we have a different number. Okay, so what do we got? I think part A is okay. We're developing an equation around the perimeter. 2 lots of x plus 2 lots of y plus the circumference gives you 500 metres. Okay, and so we make an equation for that. 2 lots of x plus 2 lots of y is 500 metres, and then we're rearranging to get y by itself. Okay, that's that equation there. When we think about the area, right, we've got 2x times y, that's going to be the area of the rectangle plus the area of the semicircle. Okay? That part there, area of the semicircle, and then we're substituting in y. That's the reason we found y over here, so we can bring it up here. We're going to expand that, and then collect like terms along here. Okay, they're like terms, we can collect them, and we've got the area function according to how it says to have it. Part C, use calculus methods to find the value of x that maximises the area. Okay. Well, calculus techniques mean we need a sign diagram of the derivative. Now we need a label for that, by the way. Don't just have a sign diagram just sitting there. This is the sign diagram of a dash of x. We only consider positive values of x because the dimension can't be negative. Okay, so that's why this is 0. I know it's a maximum because it says so in the question, so that means my sign diagram is going to be a maximum. And here the maximum point occurs when the first derivative equals 0. We move those two over, we factorise the x, and then we divide it both sides by that there. Alright? So if you want to like practice this, a question like this, okay, it's asking those exact questions, you can just change this number. Okay? How can we check to see if we got the right answer? Well, let's graph the area function. And notice how they give you the area function. Alright, so even if you can't do part A and B, you can still answer part C using your calculator. So I've got 500x, 500x, take pi on 2, x squared, and then take 2x squared. Alright, so I'm going to need to crank my V window out a bit. So let's go to 10 for x, and for y, let's go to 100 or something like that. Even more. It's area of shape, so oops. I need to crank x out as well. And y again. So you just keep going till you can see it. Okay, there we go. And then you can just go g solve max of the blue function. All right, that x value is 2070.01. And watch what happens when I do 500 divided by pi, 4 plus pi. 70.01. Okay? So you can get that 70.01 from the calculator. You can get sine diagram and so forth from the calculator. But the trick with this one is it asks you to find the value exactly. Okay, so that means you can't just write x equals. You might get 1 mark for that. Alright, but this is sort of a 3-mark question. It wants you to find the derivative, draw the sine diagram, and then perform that algebra to get x by itself. Okay? Alright, let's do a kinematics one. So I'll leave them hanging out here and get ready for a kinematics problem. So when we've been doing kinematics problems, we've been doing them with cubics, and that's what you've seen in the past few tests, is that there's been cubic functions. The one in the test is a quadratic, okay? So that makes it a little bit easier, there's less sort of calculations involved. So we have a displacement function, and it is some quadratic, okay? Part A, find velocity and acceleration. Okay, well if this is the displacement, then the velocity is going to be 2t take 5, and the acceleration is going to just be 2. Alright? Draw sine diagrams of both of them. Okay, so let's practice using our calculator to support us with this one, because I've said we can do it and I've sort of made manual arguments throughout. So the main function is x squared, take 5x, and then plus 4. Okay, now we're interested in the first derivative. Okay, that's going to be the velocity function and the second derivative. So I'm going to do that. I'm just going to change my view window again as well. So let's go just from 0 to 5, and then y, we'll just go, minus 20 to 20, something like that should be satisfactory. Okay, so the red function, all right, that's my second function. If I exit out, the red function is d on dx of y1. All right, that's graphed this function for me, 2x take 5. And what you can see from it, from the red function, is it crosses the x-axis here. I'm going to g-solve the root of it. When you have two functions, you have to sort of select which one you want to find the root of. X is 2.5. Of course we know that's true. All right, we have 2t take 5 is 0. We have 2t is 5. T is 5 on 2, which is 2.5, isn't it? So the sine diagram of the velocity function has a root at 2.5, and you can see it goes from below the x-axis to above. Below the x-axis to above. How else do we know that? It's the equation of a line, and it has positive slope, which means it's like that. Below the x-axis, then above, and that's the root. Okay, so we can construct both. If we have a of t equals 2, this is the equation of a line that says it doesn't matter what the x value is, y is always 2. All right, and you can see from the green line there, it is always above the x-axis. All right, so that's part A. You get sort of good 4 marks there. Part B, find the initial conditions. So that means the initial displacement, initial velocity, initial acceleration. Okay. So when time is 0, displacement is going to be 4. When time is 0, the velocity is going to be minus 5. And when time is 0, it doesn't matter what the value of time is, the acceleration is always positive 2. All right, and we should put some units there. So in the question, we're going to be given units. We'll probably be given like centimeters and seconds, or maybe meters and minutes, or something like that. So displacement is always the distance, velocity is always the distance per period of time, and acceleration is always distance per period of time squared. Okay, so make sure we're doing that there. Okay, part C, find when speed is increasing. Well, speed is increasing when v of t and a of t, now don't forget to label them, bad habit up here. When v of t and a of t have the same sign on their sign diagram, so they're never both negative because a of t is never negative, but they're both positive when t is larger than 2.5. Okay, v of t is positive and a of t is positive when t is larger than 2.5. Okay, but D, find when it changes direction. Okay, so this particle is going to change direction when the velocity changes from negative to positive or positive to negative. Why is that? If we have negative velocity, we're moving to the left. If we have positive velocity, we're moving to the right. And so it changes direction when time is 2.5. Okay, so that's when it changes direction. The question is, when does this occur? Where does this occur? What is the displacement when time is 2.5? So we need to take that time value and put it back into the original function. I'm going to do it straight on the graph. I'm going to try and make a connection on the graph for you guys as well. So here's the graph of the displacement function. Let's unselect that and unselect that. Okay, this is the graph of the displacement function. All right, you can see it has a minimum. So I might point at it a little bit and try and make a point. So it's like this, isn't it? So initially, the initial displacement is 4 centimeters. Okay, initially it's 4 centimeters from the point of origin. Okay, the value on the y-axis represents the displacement. Down here, okay, that's the furthest it goes to the left. It has negative displacement, so we know it's left of the point of origin. And then it starts getting closer and closer to the right, and even moving further away from the right. Okay, so what that means, that point there, that's going to be when time is 2.5. That's when it changes direction. We g-solve that minimum. We've got x is 2.5, and the y value is minus 2.25. So when time is 2.5 seconds, the displacement is minus 2.25 centimeters. All right, it's 2.25 centimeters to the left of the point of origin. Okay, part E, draw a motion diagram over the first, let's say 5 seconds. Okay, so we have S of 0 is 4, we have S of 2.5 is minus 2.25, and S of 5, let's go 6, so the first 6 seconds. When time is 6, I might need to crank my view window out a bit. When time is 6, what's the displacement? 10. Okay, so if we're going to draw that on a motion diagram, remember a motion diagram is an axis. Here we've got time is 0. It moves 2.25 centimeters to the left. So what do we need? We need 10, we need 4, and we need minus 2.25. Okay, this is where it starts. When time is 0, it's at 4 centimeters. When time is 2.5 seconds, it's at minus 2.25 centimeters, and it changes direction and moves to the right. And after 6 seconds, it has a displacement of positive 10 centimeters. This describes its position. Okay? That's part E. And then part F, find how far it has travelled in total. Alright, so it starts here and it moves to the left. So that's 4 units plus 2.25 units. It's travelled 6.25 centimetres to the left, and then it's travelled from there to positive 10. Okay, well that, from there to 0 is 10, and then that's 2.25, so that's going to be plus 12.25. We can add that together. The total distance that it has travelled is 18.5 centimetres. So I think we've had a bit of exposure to those kinematics ones. It's asking the same sort of stuff. You can just practice them a bit if you want. I can provide some more. Cool. Any questions? You guys are very enthusiastic.